We have some idea about the measure or measure theory, that is, say, mu, which is defined on a particular measure space. Measure space means, say, a whole space or sample space or a big set, say omega, and there might be a sigma field which is generated from this big set, generated by class of subsets of omega, and we have defined a measure. Now the question is that the end of definition of a measure or definition of a function, or can we generalize this function? The more importantly, the thing is that here today we are going to discuss that it is possible to consider an extension of this measure. Now, what is the meaning of extension and how we can extend it? So, if we extend, what would be the form of that function? So, these questions will automatically arise. And above all, the most important question is that if possible, if we can extend one measure under certain conditions, then whether this extension will be unique. That means if there two ways to extend the same measure on the same space, or the form of the extension would be unique. Now, of course, it would be interesting only when it is unique. Otherwise, you can have many extensions and it will be very difficult to work with. So this is the crucial thing or the subject matter of today's discussion. So, measure extension and the concept of outer measure. So, here we are not going into the details of the theoretical derivations, but little bit of theory and mainly few concepts we are going to discuss. The objectives are mainly we are going to introduce outer measure, we will define it, and we will discuss two theorems related to outer measure or measure extension more importantly. So first let us define what is the meaning of an outer measure. So we define outer measure and we denote this by mu star as an extended real valued set function. Now remember, it's an extended real valued set function, so it can take infinity, defined on all subsets of omega, satisfying more or less the same axioms that we have seen in case of while defining a probability measure, but with little more relaxation. So on all subsets of omega satisfying, mu star phi is 0 where phi is a null set. Mu star is monotone, that means if A is a subset of B, this will imply mu star of A is less than equals to mu star of B, and mu star is countably sigma subadditive. That means subadditive means mu star of union n equals to 1 to infinity is less than equals to summation n equals to 1 to infinity mu star an. So remember that here we are not writing equals to, so it's sigma subadditivity and it's a countable union, that's why we call it countably sigma subadditivity, so it's less than or equals to. So here is slight generalization of the strict condition that we have seen in case of probability theory or other functions, but monotonicity is exactly same, and also mu star of phi is equals to 0. So this we call outer measure. But before coming into the outer measure or the construction of outer measure, we will discuss a few other things. There is one important theorem, but before that let us define a set E to be a mu star measurable if for every A which is a subset of omega, mu star A can be written as mu star A intersection E plus mu star A intersection E complement. So this is the way we define a mu star measurable set E. That means we split this A in terms of E as A intersection E and union of A intersection E complement, and it is just like the same kind of disjoint union kind of thing. So mu star A equals to mu star of A intersection E plus mu star of A intersection E complement. Now the much awaited theorem. Let mu be a non-negative set function on a field F, and An is a sequence of sets. Each An is a subset of script F, that means the field. Then we claim that the following are true. First one is, if An is a disjoint class of subsets, here we have mentioned only An to be a sequence of sets which is a subset of F or belongs to F. So here we put additional restriction that An is a disjoint class of sets, and also union of An equals to 1 to infinity is a subset of another set that is called A naught. Then mu of A naught is greater than equals to summation mu An equals to 1 to infinity. And if we can get a value of m is an integer, such that A naught is a subset of union of An equals to 1 to m for some m, that means there must exist one m, then it can be shown that mu of A naught less than equals to summation n equals to 1 to m mu of An. So remember, the first part of the theorem is related to union of a sequence of sets which is contained in A naught, and the second part of the theorem is related to the set A naught which itself is contained in union of finite union of sets. So let us see how to prove this result. So one thing it is clear that it seems that we can define, or we can try to find out two different sets. Each one is union of An, the sequence of sets which is a subset of F, which belongs to F, and we are going to get the upper bound and lower bound in terms of the mu value of this An, that means summation of mu An. So first part gives a lower bound of mu A naught, whereas the second part gives the upper bound of mu A naught. Now note that the proof is obvious if mu of A naught is infinity. As we have already mentioned that it's a non-negative set function and we are dealing with extended variable function, so it can take infinity. So the proof is obvious if mu of A naught is infinity. Now we have to prove when mu of A naught is less than infinity. So first assume that, now for the rest of the proof we assume that mu of A naught is less than infinity. Clearly A naught minus union of N equals to 1 to m belongs to script F. One thing is that this belongs to, sometimes I write subset or belongs to, basically it means that this entire set is an element of this script F, which is a field. Then it's a non-negative set function. So if we take mu of this quantity or this set, that means that will be always non-negative. So 0 less than equals to mu of A naught minus An union of An equals to 1 to m, which is equals to mu of A naught minus mu of union An equals to 1 to m. This can be done by elementary set operations. It's very easy to show. And mu of union of An is nothing but summation mu of An equals to 1 to m. So what we get is that 0 less than equals to mu of A naught minus n equals to 1 to m mu of An, which means mu A naught, if we consider this thing on the right hand side, transfer this thing to the right hand side, we get mu of A naught is greater than equals to summation mu An equals to 1 to m, which goes to n equals to 1 to infinity mu An as m goes to infinity. So as m goes to infinity, this upper limit goes to infinity, that means whatever remains is the converging value. So mu A naught is greater than equals to, as m goes to infinity, is greater than equals to summation mu An equals to 1 to infinity. So that completes the proof of the first part. So note one thing, that the proof starts with a finite union of An, that is very important, but which is not directly related to the proof or the statement of the proof, but this is actually seen in the statement of the second part, but we should start with this finite union and then let m goes to infinity in order to complete the proof. So this is one technique, and this technique can be used in many times in this kind of dealing with measure or set theory or non-negative functions, set functions. To prove second part, let A naught is, we can always write A naught as union of A naught intersection n, disjoint A naught intersection n equals to 1 to m. That means, again we can write this as A naught A1 union A naught A2 A1 complement union and so on A naught am minus 1 complement up to A1 complement. So if we note the nature of this union, we can immediately write the following. But first note that this non-negative set function that we are working with mu, which is this is monotone. Since this is monotone, we always have mu of A naught intersection A1 is less than equals to mu A1, because A naught intersection A1 is always a subset of A1. So by monotone property of this non-negative set function mu, we can immediately write mu of A naught A1 less than equals to mu A1. Similarly, mu of this quantity A naught A2 A1 complement is less than equals to mu of A2 and so on. Finally, we get mu of A naught am minus 1 complement up to A1 complement less than equals to mu am. Now, from the first line, we see that these are all disjoint unions. So mu of A naught equals to mu of A naught A1 plus mu of A naught A2 A1 complement plus up to mu A naught am minus 1 complement to A1 complement, which is less than equals to, now each term, if we look at each term, we got some result for each of these terms on the right hand side, which means that it is less than or equals to mu A1, the second term is less than or equals to mu A2, and the last term is less than or equals to mu am. Thus we have mu of A naught less than equals to mu A1 plus mu A2 plus mu am, which completes the proof. Now the next theorem is very important. Actually, this theorem deals with the extension of a measure that we are going to define. So let's start with a non-negative set function, that is mu, defined on a semi-algebra script L. Then it can be shown that there always exists a unique extension. This unique is very important. Unique extension nu of mu to the field script A that is generated by script L, such that nu is additive. That means we initially have a semi-algebra script L and a non-negative set function defined on that. Then from there we can extend, or we can define a extension nu of mu to the field script A that is generated by L, such that nu is additive, and more importantly this extension nu of mu is unique. Moreover, if mu is sigma additive on L, then it can be shown that so is nu on A. So if mu is sigma additive, then this same property will be transferred to nu to the extension of mu. Now the proof is slightly, we have to put different arguments. So let script Q be a class of all finite union of disjoint sets in L, in script L. So we have a semi-algebra script L. So from there we consider the different disjoint sets and consider all possible finite union of those disjoint sets that can be formed from script L, and let us call this entire class as script Q. And for every capital A belongs to script A has a finite partition n equals to 1 to m in L. That means when script A is being generated from L, so if we take another set from A, we will always find a finite partition of this set an. This partition is finite, but this an always belongs to script L. Now let us consider this kind of A. That means for a particular capital A that belongs to script A having a finite partition in L, we defined nu A as summation mu of n equals to 1 to m. So this is the definition, or this is the way we construct nu A. This is our proposal. note that if capital A, now the thing is that we need to investigate, or we need to study this nu A, what kind of set function this nu A can be. So if capital A belongs to script A, has two distinct finite partitions. Let's call one is an equals to 1 to m, another is bj, j equals to 1 to k, all in L, all in script L. That means we can write A in terms of two different sets of sets from L. But these two partitions are distinct. Then it is clear that just a little bit of algebra, nu A equals to nothing but summation n equals to 1 to m mu of an. That means in terms of the first kind of partition, you can always write this as mu of A intersection an summation n equals to 1 to m. Whenever we introduce A, then we can think of, now replace A by its partition of the second kind of partition, that is in terms of bj, which gives us immediately summation n equals to 1 to m summation j equals to 1 to k mu an bj, because these partitions are disjoint. So when you take the mu, it will give you the summation of mu. Now again this is equals to, so we just interchange the summation notation because this entire thing is finite. So there is no problem in interchanging j and n. So here first we take the sum over j and then over n. Now we change it to first take the sum over n equals to 1 to m and then j over j equals to 1 to k mu of an bj. If we consider the first block, first sum, keeping j fixed, bj fixed, sum over n will give us mu of a intersection bj, j equals to 1 to k, and again this is exactly same as summation mu of bj. So what we get is that even if A has two distinct partitions, one in terms of an equals to 1 to m and another in terms of bj, j equals to 1 to k, but the representation of VA is same exactly. Whatever we write in terms, whether we write in terms of ans or in terms of bj's, nu A is exactly same. Nu A is summation, so nu A actually becomes summation mu an, which is equals to summation mu bj, which indicates that nu is consistently defined on A. So this is very important. So there is no ambiguity in the definition of nu A. Whatever be the partition, we will always get the same value. Now that means it is in some sense it is actually unique. So that is very easy to show that nu is additive on script A and is also unique. Now the next part is little, again there are a few arguments. So now suppose mu is sigma additive on script L and n greater than equals to 1 is a sigma partition in script A of capital A belongs to script A, and Cn n equals to 1 to m is another partition of A in script A. So now although, so we know that whenever we have a semi-algebra script L, we have defined mu on that. Now if we impose extra condition that mu is sigma additive, and now we are moving on to the class of sets script A that is being generated by the class of sets of script L. So we consider on script A, we take one set A from script A and consider an to be a sigma partition and Cn a finite one, n equals to 1 to m, to be another partition of A, and this A belongs to script A. This is very important. So now we are moving on to script A. We are looking at the sets inside script A. Again, also suppose for each n bj, j n minus 1 less than jn be a partition of an in L, because everything is coming from L. So we can expect that for each L, bj would be a partition of an which is in script L with of course j not equals to 0. Then it can be easily shown that bj j greater than equals to 1 is a sigma additive of capital A in L. And then again the same kind of logic we will put here, which gives us summation n equals to 1 to infinity nu of an, which is equals to, since bj is a partition of an. So we can write summation j equals to jn minus 1 plus 1 to jn mu of bj, and there is one summation n equals to 1 to infinity. Now this together we can easily write j equals to 1 to infinity mu of bj, but ultimately it boils down to that with j naught equals to 0. So if we put n equals to 1, then this becomes j naught is 0, so 1 to j1 and then and so on. So ultimately it will cover the entire all the sets, all the natural numbers j equals to 1 to infinity. So the sum becomes summation j equals to 1 to infinity mu of bj, which is in fact equals to summation j equals to 1 to infinity mu of a intersection bj. Now whenever I introduce a here, and we know that there is a partition of a, finite partition of a inside in script a, which is nothing but cn n equals to 1 to m, we can always write instead of a, and because of the sigma additive or additive set function property, we can write summation j equals to 1 to infinity, it remains as it is, and then instead of a we can write in terms of partition cn, that is summation n equals to 1 to m mu of cn bj. Now again if we combine these two, then what we get is n equals to 1 to m mu of cn, which is equals to mu a. So what we get is that if an is a sigma partition of script a of a set capital A that belongs within script a, then mu of a can be written as summation n equals to 1 to infinity mu of an, that means in terms of that partition of an and in terms of the measure that we have defined, there is nu, which is an extension of mu. So that actually completes the proof of this theorem, that if mu is sigma additive, so nu is also sigma additive on script a, and this proves that nu is sigma additive because nu a equals to summation n equals to 1 to infinity mu of an. So the proof is complete. Now we will complete this entire thing by putting one small remark, but the remark is the basis of further discussion. For each subset A, which is a subset of the big omega, in probability it's the sample space or the big set, the whole set, we define a set function nu A as the infimum over Sn summation mu of Sn n equal to 1 to infinity, such that n equals to 1 to infinity Sn union of Sn contains A. That means A is completely covered by the sequence of sets Sn through its union, and each Sn belongs to script L for all n greater than equals to 1. And if we consider the summation mu of Sn n equals to 1 to infinity, that means sigma additive, and we take infimum over Sn sequence of sets, so we get one new thing, that is nu A. And in this expression, what is mu? Mu is a measure defined on a class of sets script L. Now just only one thing, there is a chance that there might not exist any such covering sequence Sn of capital A. That means whenever we pick up any set from script A, we might not get any such covering in terms of Sn, where each Sn must belong to script L. In that case, we take mu A equals to infinity. So here from measure we immediately see that again this is an extended real number. So this is defined on extended real number. So in that case we can take nu A equals to infinity. Otherwise we can take this expression of nu. So this is the so the definition of nu A is complete, and this set function nu that is defined on the sigma algebra of all subsets of omega is known as outer measure induced by mu. So basically it is kind of extension of mu that is defined on script L. This is the way we can define, and it's an extended real number, that is nu A, because nu A can take the value infinity when no such at least at one particular case, which is when there is no such covering of script sets exists. So this is called the famous outer measure, but this outer measure is induced by mu. So now there are plenty of theorem and plenty of researches going on or developing new mathematical results in this area using this outer measure, but it is important to know that this is nothing but a measure extension, and this extension is sometimes given a mu, might be unique. Last one is the famous Carathéodory extension theorem. This is again an extension theorem which shows the uniqueness of the extension. That is, if mu is a measure on a semi-algebra scriptal of subsets of omega, then we can always construct, that is, there exists a measure extension nu of mu to sigma of scriptal, that means sigma field generated by scriptal. The existence is always possible. Moreover, if mu is a probability measure or even a sigma finite measure, then V is also like that. That means if mu is a probability measure, nu can be treated as a probability measure, or mu is a sigma finite measure, then nu can be treated as a sigma finite measure. And the most importantly, as I have already mentioned many times, that this extension of nu from mu is unique. This uniqueness plays a very important role in this area. So this is the famous Carathéodory extension theorem. So as I already stated at the very beginning and during the last few minutes, we have seen that it is always possible to extend the measure. Of course, there might be certain structure on which we are going to define the measure, but it is always possible. And moreover, the extension, when we are going to extend this measure, we can think of it as an extended real valued function, which is very important, number one. And number two, the most important thing is that we have seen the extension is unique, and eventually we get a very famous celebrated theorem that is called Carathéodory extension theorem, which deals with the uniqueness of this extension and the construction of this extension measure of mu. So uniqueness property is there, and that makes our life simple to work further with this extension, because whenever we extend given a particular structure, the extension would be unique. So that will make our life simple.